In this video, I'm going to solve a problem which is a direct application on Hooke's law. So we have an experimental method is applied in the physics lab in order to determine the stiffness constant K of a spring. Sammy and Sally use the following materials. A spring S having a free length L0 equal 10 centimeter، يعني هيدا الانيشال length لإله لهيدا السبرينج أو free length لإله is L0 equal 10 centimeter. A graduated ruler to measure the length of the spring. We use the ruler in order to measure the length of the spring. We have different masses marked, such as one is 100 grams, the other 200 grams, 300 grams, and 400 grams. Sammy suspends successively and separately the marked masses from the free end of the spring, and his friend Sally measures for each marked mass the final length of the spring. يعني بيجي سامي أول شي he suspends 100 جرام then he leaves it to become at rest at equilibrium. بتيجي سالي بتعمل it measures the new length as you can see إنه upon adding a mass أو suspending a mass from the spring expands. Okay, فإذا سالي measures the new length of the final length of the spring. بيرجع بيشيل 100 جرام بيحط 200 grams and so on. We denote by L the final length of the spring. The measurements are tabulated in the table below, in the following table. عنا different masses in grams, then we convert the mass into kilogram. L, which is the final length, is given in 10 centimeter. You have to calculate the weight, you have to calculate the tension and the difference in length, or we call it the expansion of the spring upon suspending a mass from it. We suppose in each case that the marked mass being is in equilibrium and two forces acting on it are the tension and the weight. We know that already. As I'm studying this object, what are the two forces acting on the mass? And the tension by the spring on the mass, will weight by the earth on the mass. وبما أنه it is at equilibrium، يعني according to the equilibrium condition, whole two forces are opposite forces having equal magnitudes. فإذا هون عم بيقولوا لنا write the condition of equilibrium of the marked mass. السوليوشن لما نقول condition of equilibrium هون بدي شدد ما بجيب سيرة الماجنتيود، بكتبها كvector relation. هيدا هو condition of equilibrium. So T vector plus W vector equal 0 vector. نيجي للmasses. To convert from gram to kilogram we have to divide by 1000. يعني 100 is 0.1, 200 0.2, so on. هيدا بالنسبة للماس. Concerning the length L centimeter اللي سالي measured it، اللي هو final length of the spring after suspending the mass from it. 10 12 14 16 18. يعني as you can notice إنه كل ما الماس كان أكبر كل ما الإكسبانجن أو كل ما الإكسبانجن للسبرينج بتكون أكبر. it expands more to a taller length. الweight we have to apply the formula W equal M times G in order to multiply it. So نحن إذا ما حاطين mass يعني الM 0, so W is equal to 0. For the second case 0.1 times G is given 10. 0.1 times 10 is 1. 0.2 times 10 is 2. 0.3 times 10 is 3. 0.4 times 10 is 4. هون نحن we are applying W equal M times G. For the tension بما أنه it's given to be at equilibrium, and we know that in equilibrium the opposite forces have equal magnitude. يعني T magnitude without vector is equal to W, so they are equal to each other. Delta L is calculated by applying the formula of L minus L0, where L is the final length and L0 is the initial length of the spring without suspending any object from it أو free mass free length بنسميه. So L minus L0 هو initially its length was لما أنا ما حاطة mass قد إيه كان اللينث لإله؟ هذا هو initial length، هذا هو free length. من هون طلعته. It was not given directly. We have to conclude it إنه لما أنا ما عندي mass هذا هو free length. So expansion هي مثلا for the second case هون 0 ما في expansion. For the second case 12 minus 10 is 2 centimeter. 14 minus 10 4 centimeter. 16 minus 10 6 centimeter. 18 minus 10 8 centimeter. Draw the curve that represents the variation of T as a function of delta L. أخذنا convenient scale هون رسمنا كل point وما بنتعدى مش المفروض إنه نحن نتعدى الvalues اللي عاطين